everybody, welcome to this video looking at the ratio and root test. So these are going to be two more tests for convergence or divergence of series. And these are especially useful if we have series whose terms look like, say, powers or factorials or roots or things like that. So let's see how it works. The first one is the ratio test, and the ratio test says that if the limit of the absolute value of an plus 1 divided by an tends to L, where L is strictly less than 1, then the sum of an is absolutely convergent. And since we know that absolutely convergent series are also convergent, this is also showing the series is convergent. On the other hand, if we look at the limit of an plus 1 divided by an, take the absolute value, we get L, which is strictly larger than 1, then the series is divergent. And then in the middle, if L equals 1, then anything can happen. So the test is inconclusive. So you can have series where an plus 1 over an tends to 1 that are convergent, or you can have series where that happens that are divergent. Okay, so as I said before, this is good for exponentials or factorials. For instance, here is a typical example. Test the sum of -1 to the n cubed divided by 3 to the n for absolute convergence. And we see we have some powers with the n cubed and the 3 to the n. So an, remember, is the thing we're summing. So then we have to do an plus 1 divided by an. So an is -1 to the n times n cubed divided by 3 to the n. To get an plus 1, all we have to do is just replace all the n's by n plus 1s. So we're going to get some negative signs, but that's in an absolute value, so that's going to disappear. Then we have n plus 1 cubed divided by 3 to the n plus 1. And then we have to divide by an, and dividing by an, which is a fraction, rather we can flip and multiply. So we're multiplying by 3 to the n divided by n cubed. So here is what we get. And then we can try to cancel. And we looked at the like pieces. So we have n plus 1 cubed divided by n cubed. That's going to be, if we take the cube out, n plus 1 divided by n all cubed. And then we have 3 to the n divided by 3 to the n plus 1. That's going to be 1 over 3. Okay, then we take the limit, the n plus 1 over n, which is the same as 1 plus 1 over n. That part tends to 1, so 1 cubed is 1. Then we just have left the 1 over 3, which is strictly less than 1. So an plus 1 over an in absolute value tends to some number which is strictly less than 1. So by the ratio test, this series converges absolutely. In particular, it also converges. Okay, so we see the steps are pretty mechanical, right? We just have to compute an plus 1 of an, take the absolute value. We can get an plus 1 by taking the formula for an and replacing all the n's by n plus 1s. We try to simplify things, and then we take the limit of that sequence. If we get something which is strictly less than 1, then the series sum of an converges. So it's relatively mechanical if we can take limits. Okay, let's see a more complicated example. So useful to keep in mind, the limit as n tends to infinity of 1 plus 1 over n to the n is equal to e. So I believe we saw this somewhere in calculus. This is a non-obvious limit, so this is just worth knowing. 1 plus 1 over n to the n tends to e, as n tends to infinity. And also the limit as h goes to 0 of sine h divided by h is 1. So I believe this one was also in Calc 1. When you look at the derivative of sine, you need this formula. Okay, so let's see a more harder example with the ratio test. Let's test the sum of n to the n divided by n factorial for convergence or divergence. So the terms are pretty complicated, but there are powers and factorials. So let's try the ratio test. So we have to look at an plus 1 divided by an, absolute value. Okay, here there are no signs, so we're not going to have to worry about that. Everything is positive. If we look at an plus 1 over an, okay, an plus 1 is n plus 1 factorial is n plus 1 to the power of n plus 1 divided by n plus 1 factorial, right? We take all the n's, we replace them by n plus 1s. And then dividing by an, we flip and multiply. So rather than dividing by n to the n over n factorial, we multiply by n factorial over n to the n. And then so that we can actually hope to cancel some of these terms, I split the top. Rather than having n plus 1 to the power n plus 1, I wrote it as n plus 1 to the n times n plus 1. So rather than multiplying n plus 1 by itself, n plus 1 times, we first do n times, and then we do one more time. And then on the bottom, n plus 1 factorial, you can write that as n plus 1 times n factorial. Then the piece on the right is the same. And now we can make some cancellations, right? So we have an n plus 1 and an n plus 1. Those are going to cancel. We have an n factorial. We have an n factorial. Those are canceling. So we are just left with n plus 1 to the n divided by n to the n. And if we bring out the power n, this is the same as n plus 1 divided by n, all to the power of n. And n plus 1 divided by n is the same as 1 plus 1 over n. So we have 1 plus 1 over n to the n, which tends to e as n tends to infinity. Okay, so what have we done? We found the absolute value of an plus 1 over an. This tends to e. And now e is strictly larger than 1. So this series diverges by the ratio test. Okay, so this was a more tricky example, but the steps are the same as long as you remember the first formula here. Maybe in some other examples you want to remember the second one. Okay, unfortunately, the ratio test is not great for rational functions. So for instance, if we did 1 over n, then in this case, an plus 1 over an would be n divided by n plus 1, which tends to 1. Or if we look at bn, which is 1 over n squared, then bn plus 1 divided by bn will be the same but with squares. N squared divided by n plus 1 squared. This would also tend to 1. So it's inconclusive for things like the sum of 1 over n, the sum of 1 over n squared. So we can't just use the ratio test for everything. There are a few examples, also there are some examples where it does not work. But at least if we're testing for absolute convergence and we have things with factorials or with a lot of powers in, then it can be worth trying. It could be quite a powerful tool. Okay, next up is the root test, and the root test is basically the same as the ratio test, except instead of taking the limit of absolute value an plus 1 over an, we take the limit of the nth root of the absolute value of an. So we take the absolute value of an, we take the nth root, we look at what limit we get if we get one. If the limit is less than 1, the series is absolutely convergent. If it's bigger than 1, the series is divergent. And if the limit is equal to 1, the root test is inconclusive. So it's very similar in flavor, it's just the thing we're taking a limit of it is different. And this is very good for things that look like something to the power of n. So it could be anything on the inside, but if the terms you're summing look like something, all to the power of n, then taking the nth root is going to let you get rid of that power of n. So it's going to simplify things a lot. For instance, here's a pretty typical example. Test the convergence and divergence of the sum of 2n plus 3 over 3n plus 2 all to the power of n. So, okay, it looks like something to the power of n, so maybe we use the root test. If we do the nth root of an, that's going to cancel this nth power. We just get 2n plus 3 divided by 3n plus 2, which tends to 2 over 3. And 2 over 3 is, of course, strictly less than 1. So the root test is going to say that this series converges absolutely. In particular, it converges. Okay, so that's it for this time. We talked about the ratio test, we talked about the root test. These are two important tests for absolute convergence and divergence of series. Yeah, see you next time, everyone. Thank you.